All right, let's get started with lesson 11, structures of acids. Now, in this particular lesson, we are going to focus on three factors that affect the overall strength of an acid. They are polarity, 2, strength of the hydrogen and conjugate base bond, and the stability of the conjugate base itself. We're going to first look at the effects of polarity. Now remember that a polar bond is created due to electronegativity difference within the two atoms that create the bond. So if a molecule will only act as a proton donor if basically the H atom has a partial positive charge. And the only way we create this partial positive charge is due to having a polar bond. So the hydrogen that we're looking at, if it forms a polar bond with the conjugate base, so that this bond is polar, due to the difference in electronegativity values, then the hydrogen will be slightly positive and the conjugate base at this point would be slightly negative. All right? Now, by hydrogen having a slightly positive charge, it allows for this hydrogen to be acidic, and therefore it can be donated to a base. Now, if the bond is nonpolar, then it will be neither acidic nor basic in aqueous solutions. For instance, let's look at an example of CH4. Okay, now CH4, if you draw the structure of it, looks like so. Now, each of these bonds, if you remember, is not really polar because carbon and hydrogen have very, very similar electronegativity values. So, therefore, these hydrogens are not going to be acidic hydrogens because there's going to be no partial positive charge on those hydrogens. So, methane is a very, very, very terrible acid. And very unlikely that it's going to give up its protons at all. Okay? On the flip side, let's look at something like hydrochloric acid, HCl. Now, the electronegativity difference between chlorine and hydrogen is pretty great. That's going to create a polar bond here, making the hydrogen slightly positive and the chlorine slightly negative, making this hydrogen acidic and easy to donate to a base. All right, so that's how we kind of look at polarity and nonpolar bonds in acid strength. All right, now here's some other ideas to think about as far as polarity goes. The more polar the HA bond is, in a molecule, the stronger the acid is going to be. All right, so you can kind of think of looking like this. If you increase the electronegativity difference, between the HA bond, okay, so between this, the bigger the difference is, then the stronger the acid is going to be. So the strength of acid is going to increase, okay, as the electronegativity difference goes. So you can kind of see that in many aspects when we look at these chemical bonds, especially going across the periodic table, okay? And so bond polarity is going to be a major factor in determining the acidity of the acid going across left to right across a period, all right? So electronegativity difference in acid strength is more prominent and more important as we move across the periodic table, all right? So for instance, let's take a look at a couple of examples of this. let's say, let's use, again, a CH bond. Let's do an NH bond. Let's do an OH bond and an HF bond, okay? So going across the periodic table essentially, and actually maybe what we should do is rewrite this so it looks like more going across the periodic table, CH bond, and then next we have a NH bond, and then we have an OH bond, and then we have essentially an HF bond, okay? Or we can look at it like it more like an FH bond, either way. All right, so as you'll see that the electronegativity difference is going to increase in this way. All right, so difference. All right, so we already talked about the CH bond here. It's not even polar because the electronegativity difference is not there. So so CH bonds are very, very, very weak acids. And then the NH bond, it's a little bit stronger, more acidic-like than a CH bond, but even so, it's still fairly weak, and therefore NH bonds usually denote bases. And then we get an OH bond. Now this is like in water, like H2O, where water becomes now a little bit better of an acid because we know that there is a positive charge and a negative charge, and therefore water can act as an acid and lose this proton, but it's still a fairly weak acid. And then you get to HF. Now HF, again, itself is a weak acid, but it is a much stronger acid overall than water, quite a bit stronger. The Ka value for HF is quite a bit larger than the K value for the Ka value for water itself. All right, so therefore going across the periodic table, knowing the electronegativity differences gives you an idea of how strong the acid is when we're starting to compare. All right, so here's another factor that's really important, especially as we go down the periodic table in a group, and that is the strength of the HA bond, okay? So the stronger the HA bond is, the weaker the acid. And that should sort of make sense to you, because if this is a really strong bond between the H and the A, it's gonna hold on to the H very tightly, and it's gonna cause that the H is going to be very hard for it to ionize. The conjugate base just isn't going to let it go very easily. So that strength is very important there. And generally the strength of the HA bond is generally the most important factor is for acid strength is when within a group going down the periodic table, as I mentioned. Okay, so for example, group 17, the HA bonds increase as you go up a group. Okay, so the bond strength is getting stronger. So for instance, if you have an HF, so let's go down that group, HF, HCl, Br, and then HI. Okay, so the bond strength is going up. The bond strength goes up, but the acid strength then gets stronger as you go down the group when the bond strength gets weaker. So the strength of the acid increases as we go down the group. All right, and that's why we find that HF is a weak acid, and the other three acids are strong acids, okay? The HCl, the HBr, and the HI are all considered strong acids. And HI, of course, is the strongest of them all within that group, okay? Acetine is in that group, but we're not going to work with acetine. It's too dangerous. So essentially, all I want you to think about is that the strength of the bond gets stronger as you move up a group. So therefore, it becomes weaker as you. The acid strength is weaker as you go up a group, and becomes stronger as you go down a group. Okay, kind of on this relationship here. All right. I hope this makes sense to you. All right, now the last factor we're going to look at is the stability of the conjugate base, and there's a lot of factors that go into the stability of the conjugate base, but essentially, the more stable the conjugate base is, the better the acid strength is going to be, more or less. So the stability of the conjugate base is determined by the size of the ion. In other words, the bigger the ion, or the bigger the anion specifically, because anions are bases. Okay, so the bigger the anion, the better and more stable the conjugate base is, okay? And that is because the anion, the larger anion, is able to hold negative charge distribution much better, all right? So, for instance, let's look at, let's go back to HF versus HCl, all right? Now, we already said that bond strength is a factor here, but that's not the only factor. It is also the conjugate base. So if HF reacts with water, it's going to produce an equilibrium, a weak acid situation, where you're going to have the hydronium ion plus the conjugate base F minus. HCl will react with water, but it's going to be strong acid, as we mentioned, due to the bond strength, but also, as you'll see, to the stability of the conjugate base. Forms the hydronium ion plus the chlorine ion. Now, the chlorine ion is actually bigger than the fluorine ion. And because the chlorine ion is bigger than the fluorine, chlorine is more stable. And since it's more stable, it can hold that negative charge better. Because it's bigger, it can hold the negative charge better, so this becomes more stable. Therefore, HCl is a better and stronger acid than the fluorine, okay? And that's why we see such a dramatic change going from HF to HCl, is due to the fact not only the bond strength, that it's easier for HCl to lose that hydrogen, but also the anion, the conjugate base, is more stable than the fluorine due to the size and holding the negative charge distribution. Okay, so hopefully that makes sense to you. So let's look at another example. Let's say we have, well, let's compare HCl and HBr. Okay, these are both considered strong acids. All right, so we will form the hydronium plus the chlorine minus the hydronium plus the bromine minus, okay? Now, due to the fact that bromine the bromine ion is a bigger atom than the chlorine atom, that the bromine conjugate base here should be able to hold negative charge better, this negative charge, and therefore it makes it more stable. So therefore, HBr is a much better acid, a much stronger acid than HCl, because the anion is more stable, as well as the fact that it's easier for this H to be released because the bond strength here is weaker. Okay, so we got kind of two ideas going on: the stability of the atom and the bond strength itself. Okay. All right, let's fill out this table here. some important ideas that we'll look at as relationships here with acids, okay? So essentially here we got group 14, we got group 15, this is group 16, and group 17, okay? So let's look at the acids here. So carbon, CH4, NH3, H2O, and HF, okay? And then we'll have SiH4. We're just making some common substances of these elements with hydrogen and looking at their acid strength. Oops, not H2O, H2S, HCl, and then we'll go with H2SE and H2TE, HBr, and HI. Okay, so the acid strength going down a group should increase. So increasing, misspelled that. So increasing acid strength as we go down a group, and that is due to there's a weakening of the bond. Okay, so the bond gets weaker as we go down a group. Remember, so we could say the bond strength increases all right, but the stability of the anion increases. Okay, so these two factors here, the bond strength and the stability of the anion, is going to be the reason for the increase in bond strength. So we know that this is a weak acid, strong acid. This is also a strong acid and strong acid. Okay, good. And then the same thing can be said going down from water to HS, H2SE, and so forth. The acid strength is going to increase going down group 16. Also going down group 15, the acid strength increases, and so forth. Okay? Now going across the periodic table, okay, there's an increase acid strength. Okay, going across. Now, why is that? Well, that's because there's going to be an increase in electronegativity difference, okay? Electronegativity, right? All right. So again, essentially, this is neither acid or really a base. And this is, ammonia is more of a weak base. Water is amphoteric. It can be either one, but it's a fairly weak acid and a fairly weak base. SiH4 is also neither an acid or a base because they are nonpolar. This would be considered a very pH4 or pH3 is a very weak base. It's a stronger acid. than ammonia is. And then H2S is a weak acid. And then we go to our strong acid because of the electronegativity difference. Weak acid and a weak acid. Okay, so we kind of filled in this table. So basically know these kind of relationships and you'll be good to go on this. Okay, one last thing. I want to talk about carboxylic acids a little bit more. We've mentioned them in the past. So carboxylic acid, a giveaway for a carboxylic acid is the COOH group there. The COOH group looks structurally looks like this. All right, now, so this right here is the carboxylic acid group that I got highlighted here. This is the COOH group that we look at, okay? So what makes this an acid? What makes carboxylic an acid? This H right here is what makes it acidic. And why? Well, it's because of two things. One is that this bond here is going to be polar. So it makes this H slightly positive and this oxygen slightly negative. All right, and it's a pretty big difference there. Okay, and so when this H is lost, you're going to create a conjugate base that looks like this, okay, with a negative charge once it loses that, okay? Now, the conjugate base is also important, and we're going to talk about why the conjugate base is so important to allow this, to allow carboxylic acids to be acidic. I do want you to know that all carboxylic acids are weak acids. All right. Now, before we move on to looking at the anion here of this, or the conjugate base, why are these hydrogens that I'm underlining here, why are they not acidic hydrogens? Why is it this hydrogen the only one? Well, it's simply because the polarity. These are all non-polar bonds. All right, so therefore these hydrogens are not acidic in that carboxylic acid, only that one. Okay, so I'm going to erase this, and now I'm going to talk about the anion of our carboxylic acid. Okay, so the anion, which is the conjugate base, the reasoning here, the conjugate base helps so much, is because residency is involved. This double bond can also be there where that oxygen is. So we actually have a resonance structure that occurs with this carboxylic acid. Oops, already did that one. Now the double bond is on that oxygen, okay? So because of resonance structures here, okay, this is going to contribute to the stability of the anion. All right? In fact is, the more resonance structures that can be made, the more stable the anion will be. In this case, it can form two resonance structures, so it increases the stability quite a bit. So carboxylic acids have two things going for them. The acidic hydrogen that bonds to the oxygen is going to be polar, so it's easier for that H to be removed. At the same time, the anion, or the conjugate base, of the carboxylic acid is more stable due to the two resonance structures that can be formed between them. Okay, so these are all factors that I want you to understand really well about carboxylic acids as well as other acids. But this is all I have to say on this particular topic for now. So study your notes really well. Study this topic super well. It's important. Come to class with any questions, and that's it for now.